Hello everybody, and welcome to the next lecture of 6838. Today we're going to continue our discussion of the Laplace operator, but now rather than covering the theory, we're going to go over how to approximate Laplacian operators in practice. Now, in this lecture segment, we're going to focus on Laplacian operators on triangulated surfaces and more generally on meshed objects. So essentially Laplacian operators that are relevant to low-dimensional domains. And then in an additional lecture segment, we'll also cover one formula for a point cloud Laplacian, which is what appears in a lot of machine learning, semi-supervised learning style applications. So our focus of today's lecture, just like the last few, is going to be on this particular object known as the Laplacian operator. And even if you didn't follow all of the details of the last couple lectures, hopefully you get the extremely high-level point that the Laplacian is an operator that inputs a function, like f. Maybe think of f as being infinitely differentiable. And it outputs another function, which is the Laplacian of f. And both of these functions are maps from our domain into the real numbers. So in our previous lecture, we covered many different Laplacian operators, including ones on Euclidean space, a Laplacian operator on a graph. Incidentally, I noticed that my formula for the Laplacian operator on a graph had the wrong sign in our previous lecture. I'm sorry, I was so close to getting it right. But in any event, we covered Laplacian operators on curved surfaces. Now we're going to see if we can use some of the approximations we've had of curved domains from previous lectures and essentially combine them with an approximation of the Laplacian. Now, there are so many different ways to do that. We're going to cover one particular strategy today, and then in later lectures of this course, we'll see some other approaches that sometimes even lead to the same formula for the Laplacian, but they're motivated in a very different fashion. So, it's just a tiny bit of review. Of course, we talked about the basic Laplacian operator on Euclidean space as minus the sum of second derivative operators. And this was useful, for example, for answering the question of whether you can hear the shape of a drum, which has to do with the wave equation, like what I've shown you on the screen here. The Laplacian shows up in the heat equation. It shows up in minimizing Dirichlet energy, basically all over the place. Now, this Laplacian formula is probably simple enough to approximate. If we were to approximate this formula just in two-dimensional space, one reasonable thing we could do is approximate omega with a grid of points, and then our Laplacian operator, is just some divided difference on the grid. But the problem comes when we need Laplacian operators for functions on curved domains, like surfaces, point clouds, manifolds, and so on. And in fact, if you crack open a classical differential geometry textbook and you look for formulas that you might try to adapt to a meshed or a grid scenario, things get ugly really fast. So for example, here we have the Laplace operator in coordinates using kind of fancy Riemannian notation, and it's certainly not very clear how to go from this formulation to some divided difference looking formula on a curved surface. Now, that isn't to say that people haven't managed. There are many different discrete Laplacians out there, and for just about every smooth formula you can find, somebody's tried to discretize it. But the question is whether there are more natural and frankly nice looking approaches that can lead you to the same operator without all of the excruciating pain here. Now, why is this so difficult? Well, essentially, the Laplacian from the start is a hard object to work with. And hopefully you guys are seeing that we keep having the same motivation for constructions in this course, which is that we'd like things like the Laplacian, which are second derivative quantities, just like Gaussian curvature, incidentally. But the typical objects that we work with admit maybe one derivative if we're lucky, right? Like we might have a triangulated surface like the right-hand side, or even worse, just a cloud of points, in which case it's really not clear what it means to approximate a second derivative, since we just don't have two derivatives to work with. We have a surface which is piecewise flat and has these facets which are simply not differentiable two times. So today what we're going to do is cover one really important approach, and I think a side benefit of today's lecture is that this approach to solving partial differential equations and approximating differential operators like the Laplacian is one of the most common approaches in engineering more broadly. And that approach is known as the finite element method, or FEM. And essentially, we're going to cover one really straightforward FEM method known as the first order Galerkin FEM discretization of the Laplacian, where what we're going to do is approximate a function and its Laplacian in some function space, and then work through different versions of the Laplacian until we get one where our numbers of degrees of freedom match up. Now, first order finite element method, or finite element method more generally, is one of the principal ways that computers are able to solve partial differential equations in software. So we're going to cover a very simple version of it for this like second order homogeneous PDE. And one nice side benefit, I hope, is that it'll give you an idea for the flavor of techniques that people use in numerical partial differential equations at the more advanced level. So everything that we do today generalizes to, in all kinds of different ways, to different function spaces, different operators, nonlinear problems, and so on. But I think that the Laplacian is a great place to start, simply because it's fairly straightforward and concrete. So that's what we'll be doing. Now, the basic sledgehammer in the finite element method, especially for linear problems, is the same sledgehammer that we've been using for our theorems and proofs in the past couple lectures, which is integration by parts. You thought you were done with it, but you're not. You know, every time you try to leave, they pull you back in. In particular, recall that we have many integration by parts formulas that look like what we have on the top of the slide here, right? That if I have Laplacian of a function g, and I integrate that against another function f, right? That's what's on the left-hand side here. That's equal to some boundary integral. I'm going to be quite sloppy about that today, plus the integral of the gradient of f dot product the gradient of g. Now, for today's lecture, I'm mostly going to ignore these boundary terms. That's not because they're particularly hard to deal with, but just because it's like an additional mathematical headache that we have to cope with. So I'll let you guys work that out, probably on the homework if I remember. So for today, we're going to work on surfaces that don't have boundaries, or manifolds without boundaries. So think, you know, donut and sphere rather than like the patch I'm showing you. Now, why is integration by parts so critically important to algorithms or discretizations like the finite element method? Well, there's a lot of different intuitions here, and none of them is any better or any worse than any other. But in my mind, here's how I think about it. Now, the Laplacian is a second derivative quantity, right? If I compute the Laplacian of g, then I need to be able to differentiate g 2 times. But if I integrate the Laplacian of g against some other function f, then I get the formula on the right-hand side. And one of the really kind of incredible things about integration by parts, you notice your instructor gets really excited about integration by parts, is that you only need one derivative. This is amazing. So somehow we're able to integrate against the second derivative of a function and only really need to know how to differentiate one time, like compute gradients. And we've actually already seen a few times in this course, and we'll see it again today, that it's not so hard to cook up bases of functions on a triangulated surface or on a mesh that at least have one derivative. In fact, that turns out to be much easier than coming up with functions that have more than one derivative. And so somehow that right-hand side is easier to work with and somehow, I don't know, more harmonious. You know, like, you know, on the right-hand side, we've got, you know, one derivative and one integral outside of it, and somehow maybe those cancel out and give you the right space. But anyway, that doesn't matter so much. The main point is that what finite elements are going to do is leverage the fact that we can come up with a formula that only needs lower order derivatives, and then use that to cook up a method for solving PDE. By the way, when I say PDE, I think I've defined it in the past, but in case I haven't, I mean partial differential equations. Okay. So let's actually work through an example of how we might use this strategy to make our life easier when we're solving partial differential equations involving the Laplace operator. So in particular, we're going to focus on one partial differential equation which shows up all over the place, both in geometry and in many other domains, which is known as the Poisson equation. So the Poisson equation can be written as the Laplace operator applied to f equals g. So typically here, in the Poisson equation, the input here is a function g, and the output is a function f whose Laplacian equals g, right? That's the basic problem that we want to solve here. So the question is, how can we come up with an algorithm that approximates solutions to this problem when f and g are probably going to have to be approximate, right? We can't express the space of all possible functions on a computer. So one thing that we might do is say, suppose that rather than working with all possible functions, what we're going to do is introduce a basis. So we're going to introduce a basis of functions, psi 1 of x, dot, 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 psi big K of x, all of which go from our domain into the real numbers. So for example, in one dimension, if I wanted to cook up an algorithm for solving Poisson equation in 1D, maybe my basis for functions are like, functions that look like little hats centered at different points x that we can weight. So in other words, I'm like only going to work with functions that are piecewise linear in some region. In fact, that'll be exactly the basis we work with in today's lecture on a triangulated surface. Okay, then what we're going to do is assume, or suppose, whatever, that we could write our input function as a linear combination of our basis. So in other words, what we're going to do is say, okay, we'll write g of x is really equal to a sum over k of wk psi k of x. Okay, so if we can write g in the basis, then one tempting thing to do might be to say, like, okay, maybe I write g as a combination of these piecewise linear functions. Then can I figure out some approximation of my output where I can write it in exactly the same basis? So maybe I try to write f as equal to a sum over k of some other coefficients, vk psi k, so that I now have a finite number of unknowns. Rather than just some generic function f of x, I'm going to find a set of vk's so that Laplacian of f written in this form looks like g. But the basic problem here is even if I put some form on my input function g, there's no reason why the solution f to the Poisson equation should be written in at least exactly in the same form. So for example, even if I assume that g here is piecewise linear in one dimension, then I really can't assume that f is the same. In fact, if I write g in exactly the basis I've drawn for you here in 1D, well, f has sort of two more integrals than g, right? So I would need like, what, second or third degree polynomial. So the best that I can do is to give up my hopes and dreams of an exact equal sign here and instead just write an approximation. Okay, so what do I want? I want the Laplacian of f approximately equals g with the assumptions that I've made, which are that f and g can be written as linear combinations of some basis of functions. Now, we'll actually spend the rest of the lecture giving you details about one particular choice of basis, but for now, we'll leave it as abstract. Okay, so what can we do? Well, we can plug in our forms for f and g here, and what are we going to get? Well, let's actually go from right to left. So g is the sum over k wk psi k of x equals Laplacian of f, so the sum over k vk Laplacian psi k of x. And again, this is probably just approximate. Now, we have a finite number of unknowns, right? So our input is the w's, and we want our output to be the v's. But here's the problem. We'd like this approximation to be true for all x in our domain. Now, why is that problematic? For each x, I get some linear combination that relates the w's and the v's. So if there's an infinite number of x's and a finite number of k's, that's going to be a problem because there are more equations than we know what to deal with in a linear system. So here's going to be the trick, and this is the trick of the Galerkin method for solving finite elements problems. What we're going to do is we're going to introduce a test function, which is just another function also on the same domain. And in this Galerkin strategy, we're going to choose our test function to be among the psi's here. So we'll say that it's some function psi sub L. In fact, what we're going to do eventually is write the same expression for all L's. And we're going to integrate both sides of this expression here against psi sub L. So we want to integrate star here against the test function. So what am I going to get? Well, it's actually pretty straightforward. I'll get the sum over k of wk times the integral over my domain of, well, I have a psi k of x, I have a psi L of x, d area of x, equals the same kind of thing on the right-hand side. Oops, I'm sorry, I put my index downstairs instead of upstairs, for shame. So this is equal to the sum over k of vk times the integral of, well, we're going to get psi L of x, Laplacian psi k of x, d area of x. Okay, and again, all I did was take this start expression here, multiply both sides by psi L of x, right, this quantity, and then integrate over the domain M. Now, why on earth would I do such a thing? I mean, essentially, I started with this nice partial differential equation, and I'm making it more and more complicated. Well, here's what I'm going to do. I'm going to just take our complexity and hide it a little bit. Now, in particular, I can define a matrix with entries that are these integrals. I can call this M, I guess, KL, and I'll call this matrix LKL. And by our integration by parts argument on a previous slide, notice that I actually only need one derivative of the size to compute elements of L here. All right, and so what do I end up getting? Well, if I ask that this is true for every test function psi L drawn from our initial set, so for all L in 1 to big K here, well, then I get a matrix system that looks like the following. It looks like M times W equals L times V. That doesn't look so bad. And the M's and the L's here, they're functions of our basis, our basis psi, but they're not functions of the coefficients W and V. So here's a really nice thing, is that M and L are square matrices. So if I am given W, I can actually solve this linear system of equations for V, you know, under some linear algebra style condition. And that is the Galerkin finite element method. Now, what makes it first order is going to be the fact that we'll choose a particular basis of size here, which is very simple. They just look like linear functions, and we'll go through that in a lot of detail. So again, to summarize, here's what we did. We wanted to write a piece of software that can approximate solutions to the Poisson equation. And remember that the Poisson equation inputs a g and outputs an f. So now we're going to choose some fixed basis of functions that is finitely sized on our domain, and we're going to write g in that basis. We'd like to write f in the same basis, just with some unknown coefficients v, but the problem is that we can't, because we can't expect this expression I've written here to hold for every possible x. So this gets a frowny face next to it. I can't actually do that. So instead, the Galerkin finite element method does something really sneaky. It says, okay, I'm going to grab another function psi sub L from the same set here. I'm going to take my start expression and integrate both sides against psi L. And what I get, after a bit of simplification, is a finitely sized, in fact, square linear system of equations that I can solve for V. So that's our basic story, and essentially we're going to spend all of today's lecture filling in the details, like what are the elements of M and L here for a really nicely chosen basis that's quite popular in practice. Okay, so let's erase and then look at this in a nicer form on a slide here. Okay, so let's keep moving here. So let's summarize what we've done on a nicer looking slide. So here's our summary of the Galerkin FEM approach. Essentially, we start with some PDE we want to solve, like g equals Laplacian f. And we integrate both sides against the test function psi. That gives us some relationship between the integral of psi against one side, g, and the integral of psi against the other side, Laplacian f. And conveniently, this sort of lowers the number of derivatives that we need of psi and f to solve this problem. Now, in Galerkin FEM, we write f, g, and psi all in the same basis of functions, which we can say are from psi 1 to psi big K here. And after we do that, this integral relationship just becomes K integral relationships that can be summarized in this nice matrix system, M, W equals L, V. And so what do? We invert L, and we're left with a way to recover V from W. Now, the matrices involved in this problem have names. So typically we call the matrix of inner products M, the mass matrix. And we call the matrix of inner products of gradients the stiffness matrix of our problem, L. So L is kind of like a discrete Laplacian matrix, which is why we call it L here. Now, there's so many different ways to interpret what's going on in this technique. Here's yet another one. We keep reusing the same set of tools in this course, right? One of them is integration by parts. Another tool that we use a lot is variational calculus. And there's actually a nice variational calculus way of understanding what we just did as well. And that looks something like this. So suppose that we want to solve the following optimization problem. And again, we're extremely sloppy about function spaces and so on, but bear with me a little bit. Let's say that I want to minimize over all functions f on our domain the following quantity, which is the integral of 1/2 the gradient norm of f squared minus f times g. dA. So you might recall from your previous lecture that this term in this integral, this is the Dirichlet energy. And this is just an inner product, right? It just ends up looking like F inner product G. So at this point in this course, we've computed variational derivatives a million times. I'm not going to do it again for this problem. But essentially what you'll end up finding is that the local optimality conditions, like take the derivative with respect to f and set it equal to 0, are going to lead us to the Poisson equation, Laplace f equals g, if we do this in theory. But one thing that we can do is, just like we did on the board a minute ago, we can write f of x in a basis, right? So maybe we write f as the sum over k, v, k, psi, k of x. And similarly for g. So g of x equals the sum over k of wk psi k of x. So again, our input data is w, and we want our output to be v. But whereas in our previous sort of set of slides and writing on the board, it wasn't totally clear sort of what the Galerkin approximation is doing, I think this variational formulation is a little bit nicer. So let's say that we plug these bases in here. Okay, so now what's going to end up happening? Well, our minimization problem is actually over a finite number of variables now, right? Just v1 through v big K. And what ends up happening? Well, we're going to get the following, which is 1/2 times the norm of the gradient of f, but of course f is written in this basis here, so it's really the norm of the sum of vk gradient psi k minus the inner product of f and g, but now f and g can both be written in the same basis, so maybe we write the sum over k l of vk w l psi k of x psi L of x, like that, dA. If I'm going to be slightly less sloppy, there should be an x there too. So one thing that you can work out is that actually in the notation of the previous writing we were doing on the board, if we just take this square and expand it out, what we're going to end up with is a very familiar quantity. It's just going to be 1/2 v transpose LV. And similarly here, this is going to end up being v transpose MW. Okay, so at the end of the day, really what we're solving is, after we substitute in a basis here, we're solving a vector problem for v in r to the big K of 1/2 v transpose LV minus v transpose MW, which, just like before, is going to lead us to LV equals MW. Exactly the same formulation that we derived in a different way by integrating against test functions. But here, rather than integrating against test functions, what we did is just plug in a form for f and g and restrict the variables in our optimization problems to those spaces. The reason we were able to do this, and notice that we didn't need a squiggly equal sign like before, is that we're just kind of adding a constraint on our optimization variable f. Right? We're just saying that we want the f that solves this optimization problem and like to some minimum, but is restricted to work in the space of functions that looks like this linear combination here. And we ended up in the same place. This also gives a tiny bit of intuition for what the Galerkin finite element method is doing. It's somehow upper bounding the optimal objective here. Do you see that? Because essentially when I plug in this ansatz for f, right, this particular form, it's kind of like adding an extra restriction or an extra constraint on our variable f rather than, optimizing for just a generic function. So what does that mean? Well, if I add a constraint to a minimization problem, the optimal objective increases. On the other hand, this minimization problem has a finite set of unknowns, v1 to v big K. And so this thing is actually solvable, whereas our original problem was not. So anyway, this is just another sort of variational interpretation for Galerkin FEM, which is to say that if we take a PDE and write it in its weak form, like we think of it like an optimization problem, then essentially in the Galerkin FEM algorithm or discretization, all we're really doing is plugging in some finite dimensional approximation for f, adding that as a constraint to our optimization problem, and working out the optimality condition. So these are equivalent ways of understanding the same sledgehammer, and I think they're both pretty valuable. All right. Okay, so one thing that I should note before we get too far into the first order finite element method here is that although this is one way to discretize the Laplacian operator, and we'll spend basically the entire lecture on this strategy today, it's definitely not the only way. Some other methods include divided differences, higher order elements, boundary element method when your domain is flat, discrete exterior calculus we might mention later in this course. But first order finite elements is somehow a very fundamental method for discretizing PDE anyway, so I think it's worth some time. So when we talk about first order finite element, really what we're doing is we're somehow working with the dual of a function. This is, one of many notions of duality that we'll encounter in this course. The basic idea here is that when we have a function f from some manifold m into the real numbers, then there admits a dual operator, which basically is an operator that inputs another function g and gives back the integral of f against g. Okay, so when we talk about the finite element method, oftentimes what we're really doing is working with these operators rather than with these functions. So for every function f, there exists some operator L sub f, which inputs another function and gives back the integral against it. And so in the language that we've already started to use, the input to our operator is going to be like the test function, and the operator that we'll construct is the dual of maybe our unknown, our input data. And one thing that's really important to understand and to get straight is that essentially if we have so it's very easy to construct the L2 dual of a function given the function. We can actually go the other way around as well if our function is smooth. So one thing you can convince yourself at home, let's say that I have access to L sub f rather than f, and I'm trying to compute the value f of x at some x under the assumption that f is absolutely continuous here. Well, one thing that I can do is that I essentially can sense the integral of f along any interval, right, by integrating it against this weighted function g sub t. So if I take a limit as a approaches b, right, that leads to a delta function, then essentially what it gives me is a strategy for kind of sensing the value of f of x at any x by integrating f against a function g, which is getting more and more and more pointy at that function. So anyway, this argument doesn't matter a whole lot, but it's just to say that if I have this kind of complicated way to encode a function, L sub f, I really can recover the values f of x, assuming they exist. But the reason that we like working with the dual, like kind of sensing a function rather than working with it directly, is that it allows us to work with low-order derivatives. So in particular, here's our integration by parts formula again. So if I have the L sub Laplacian of v, so I want to sense the Laplacian of a function by integrating it against this test function u, essentially what I've already sketched out in this lecture is that by integrating by parts, in other words, by introducing the second formula here, we only end up needing one derivative of u and v rather than two derivatives of v. And this is just this like totally miraculous formula, which is letting us basically use the Laplacian operator without actually evaluating it, right? By only evaluating, one derivative instead of two. Okay, so in the Galerkin FEM discretization, essentially what you do is you choose one of each. You choose a function space for like your input function and your output function, f and g. And you choose another function space for your test functions. You integrate your PDE against the test function. And every time you have another test function, you end up with another condition on the coefficients of the functions of the function space. And in the simplest version, these two sets are the same, right? Like what we wrote down before, it's just all these functions psi. And again, the beautiful thing here is that just one derivative is enough. So now let's add an additional term, which is the fact that we're going to work with first order finite elements. And essentially what that's telling us is something about our choice of basis functions. So the basis that we're going to work with is something called the hat basis for functions. And we're going to start by talking just about triangle meshes. Although this strategy essentially lifts to tetrahedral meshes or any other mesh in a pretty straightforward fashion. So as our input data, we're going to be given a triangulation of our domain. It might be curved, it might be flat. And just like we've done in previous lecture, when I talk about a function, usually when I think about the input or the way that I can express a function on a triangle mesh, I can think of it as one number per vertex. Now what the hat function allows us to do is to interpret that one number per vertex of our triangle mesh, for example in 2D, as a function along that entire faceted domain. So the way that it does that is by just integrating values of the vertices, or rather interpolating values of the vertices to the interiors of the triangles in a linear fashion. In fact, if you took my undergrad graphics class, 6837, then you've already encountered this. This is exactly barycentric interpolation. So again, in the hat basis, we're essentially given one hat function per vertex, which is 1 at that vertex, v, and 0 at all the other vertices, v, and linearly interpolated across the triangle faces. So this nice visualization from my colleague Keenan at Carnegie Mellon is essentially showing us what one of our basis functions look like. Again, just 1 at a vertex, 0 at all the other vertices, and linearly interpolated inside of the faces. So when we talk about a function on a triangle mesh, like some function f of x, x can now be in the inside of a triangle. That's sort of the big novelty here. And the way that we're going to do it is that we're going to think of it as a sum over all the vertices of the value of f at that vertex, like fv, multiplied by the hat function hv evaluated at x. And one thing that you can check is, as long, if x is a vertex of our mesh, we'll have the property that hv is equal to 1 if x is the vertex v, and 0 if x is some other vertex of our mesh. Okay, so this is just a way to take one number per vertex of a mesh and interpolate it across the triangles in a nice local fashion. So now what we're going to do is work through that first order finite element method specifically for this choice of basis functions of hats. And this will become hopefully more and more clear as we work through the calculation. So I'm going to do it at a high level first, and then we're going to dive into the details. So at a high level, here's what's going to go on. Remember that I want to sense the Laplacian of a function f. So what does that mean? Well, I'm eventually going to write f and g in this hat function basis. And essentially, rather than integrating Laplacian of f against g, I'm going to work with this weak form. By the way, when we use this sort of integrated by parts version, we call it the weak form, which is the integral of gradient of f dot product with gradient of g. Now, again, remember at the beginning of the lecture, I warned you that we're going to ignore boundary terms. So we're going to just work on surfaces without boundaries. Otherwise, you might need some extra terms in your integral. I'll let you kind of logic your way out of that. Okay, so we're going to write f and g as linear combinations of these hat functions, right? So f and g are just a bunch of weighted sums of functions that look kind of like this. Now, the key observation is if I take the gradient of something that's linearly interpolated across a face, well, the gradient of something linear is constant. So what I get is just one vector for every triangle. Okay, so when I take that dot product, I get one scalar value for every triangle. And then essentially integrating over the mesh is just taking that dot product, scaling it by the area of the triangle, and summing it over all the different triangles. And that's basically it. And that's going to lead us to our Laplace operator. So that's a very high-level story, and hopefully it convinces you that somehow this value is computable. That's the start. But we're going to show that it actually takes a really nice form. We're going to do it in some detail. So let's give ourselves some space on the board here and get started. So I'm first going to just work with hat functions on a single triangle, and then we're going to consider an entire mesh. So in particular, I'm going to draw a kind of big triangle here because we're going to work with it quite a bit. Here he is. I want to make sure not to go off the side of the screen here. Okay, and let's give things some labels. So I'm going to work with a hat function f, and f is going to have the following property. It's going to have the property that f of v1, if this vertex is v1, is equal to 1. We'll label the bottom left vertex v2, and we'll say f of v2 is equal to 0, and similarly f of v3 is also equal to 0. Okay, so in our hat function here, essentially we have a simple affine function which is 1 at this vertex here and 0 at the other two vertices, and our job here is to compute the gradient. Now, here's a nice observation, which is that if I restrict f to any edge, right? So I just think of f as like a one-dimensional function varying along one of these edges. Well, assuming that f here is affine, right? Then this is still affine just in one dimension. And in particular, this is just a really straight, it's just a straight line. It looks like y equals mx plus b at that point. So in particular, one thing that we can do is look at the change in values of our function f along every edge. Now, remember that if f is linearly interpolated inside of this triangle, then the gradient of f is just a constant inside of the triangle. Essentially, what we're doing, by the way, is we're thinking of this affine model like f of x is equal to, the gradient of f, which is going to be just a constant vector now, dot product with x plus some constant. Okay? So if I restrict to an edge, then what do I find? I find that the gradient of f dot product with, for example, v1 minus v3, well, what is that? That is just the linear approximation of f, or the change of f between v1 and v3. But linear approximation is exactly what we want. So it's just f of v1 minus f of v3, so it's 1. Similarly, the gradient of f for our linear function f, dot product with v1 minus v2, well, it's equal to 1 minus 0, so this is 1. And finally, gradient of f dot product v2 minus v3. Well, both of those have value 0, so that's just 0. Okay. And by the way, if we want to, our gradient we're going to think of as a tangent vector. So if our triangle had a normal out of the plane, then we could say a gradient of f dot product the unit normal to our triangle is equal to 0. That's not going to matter a whole lot. We're just going to do two-dimensional calculations for now. Okay, so let's see here. First of all, let's draw a picture of what we have so far. And actually, the really interesting relationship that we're going to start with is this third one, which says that the gradient of f, remember that's a constant vector in our triangle, thanks to this expression here, dot product with the edge from 2 to 3 is equal to 0. Well, when dot products are equal to 0, that means that vectors are orthogonal to one another, right? So what do we know? We know that our gradient is orthogonal to this edge. And also, it points in the direction of steepest ascent, so it points up here. So our picture so far looks something like this, right? We have some vector, which is the gradient of f, and it's orthogonal to this edge on the bottom, right? And we got that thanks to this star here. Now, let's take a look at this starred expression here. And now we're going to start applying a little bit of trigonometry. So let's give our edges a length. We'll call that length L2, this length L3. And I don't think we're going to need the third edge for now. Okay, and let's use this double star thing to do something interesting. Now, in particular, what we can do is say, okay, well, if we follow this relationship here, then we're going to get that 1 is equal to this dot product, but we're just in 2 dimensions. So the dot product is the length of one thing, the length of the other thing, and the cosine of the angle in between them. Yeah? So it's the norm of the gradient of f times the norm v1 minus v3, so that's L3, times the angle between these two guys. So now we have to be a little bit careful. So let's actually give this angle here a name. We'll call it theta 3. Okay, so what is the angle between, well, let's see, between the gradient of f and the vector between v1 and v3? Well, if we kind of move the, we can take this vector and translate it any way that we want. So maybe we put it over here. So now we can see that the angle between this edge here and this edge, if this is theta 3, well, then the complement, because gradient f is rotated, is just going to be pi over 2 minus theta 3. Okay, so in particular, we have this is the norm of the gradient of f times L3 times the cosine of pi over 2 minus theta 3. Okay. And thanks to trigonometric identity, we know that cosine of pi over 2 minus x is sine of x. Let's write that. Okay. I'm going to stick to high school trigonometry for a little while here. Okay. So in particular, we can isolate the norm of the gradient of our function here. And what are we going to get? We'll get that the norm of the gradient of f, the 2 norm, is equal to 1 over 2 times L3 times sine of theta 3. Whew. So now let's label some more interesting stuff inside of our triangle. In particular, remember that the height of a triangle is just like the length of the line that starts at the bottom, goes all the way to the top orthogonally, so we'll call that h. So take a look. So what is the sine, S-I-N-E, of theta 3? Well, sine is opposite over hypotenuse, so it's h over L3. Okay, so then what does this mean? This means that we really have 1 over 2 times the height of our triangle. Okay, so that's kind of a nice formula for the norm of the gradient. It's at the end of the day, oops, Wait, why did I write a, sorry, I don't know why I wrote this 2 here. This 2 shouldn't be here. It wasn't here, so I'm not sure why it was here. It's just 1 over the height of the triangle. My apologies. Okay, that makes better sense. I'm sorry, I'm checking my notes off of the screen, and it's good that I did because I made a goofy mistake. All right, so then what do we have to do? Well, this gives us the length of our vector here, but it doesn't give us the vector itself. So let's say that we give this vector a name. We'll call this E2, 3, right? So this is just the vector from vertex 2 to vertex 3, or equivalently it's just V3 minus V2. Okay, well we have the norm and we have the direction, which is just E2, 3 rotated counterclockwise by 90 degrees. We'll call that E2, 3 perp. Okay, so what do we know? Well, we know that the gradient of f is equal to E2, 3 perp divided by its length, right? Because that's the unit vector in the E2, 3 direction, multiplied by the length of the gradient, which is 1 over h. Okay, so that doesn't look too nice so far, but let's make it a little bit nicer. In particular, remember that the area of a triangle is equal to 1/2 times the base times the height. So, for example, it's equal to the length of E2, 3 times h. And of course, the length of E2, 3 and E2, 3 perp is the same. So what does that mean? That means that the quantity in the denominator here is the norm of E2, 3 times h, which is just 2 times the area. So this is really E2, 3 perp over 2 times the area of our triangle. And that 2 actually should be there. That's not like our previous mistake. Okay, so what did we just show here? Essentially, we started with an assumption, which is that we have a function which is linearly interpolated across the triangle, is equal to 1 at the top vertex and 0 at the other 2 vertices. And essentially, because our function is linear, we could write these 3 relationships here. This is just straightforward. And that gave us a way to compute the norm of the gradient of our function, where the gradient is just a constant vector. It's nothing fancy. And in particular, once we know the norm of the gradient, we also know the direction of the gradient because it's orthogonal to the bottom edge and we're in 2 dimensions. We can just write this thing in closed form, and we get a pretty nice formula, which is that you take the bottom edge, rotate it counterclockwise 90 degrees, and divide by 2 times the area of the triangle. That gives you the gradient of a linearly interpolated function across a triangle face, which is sort of exactly what we expect. So I'm going to clear out the board really quickly, and then we'll summarize this. Actually, let's go ahead and look on the next slide. Even though I'm covering it up a little bit, hopefully you can see that our formula here agrees with the nice formula in the picture. So now that you can see that, let's erase. Okay, so now we know the gradient of a hat function. One thing that we should do is quickly note a relationship between this formula and a formula we've actually already seen. Remember when we talked about computing curvature as the derivative of surface area, we differentiated the area of a triangle with respect to the position of a vertex. We actually got nearly an identical formula. And it turns out there's a very easy reason for that. Like essentially, well, the integral of the constant function is the area of a surface, and you can write the constant function as the sum of all of the hat basis, and you'll see that it all ends up fitting together. That essentially the gradient of our hat function ends up being the gradient of triangle area just scaled by a factor of 1 over area. And this is kind of a nice link to essentially mean curvature flow, that kind of universe. But I'll let you guys think about that more at home. All right, so we now know how to compute the gradient of a function interpolated along a triangle. We're still not quite done, because what we actually needed to do finite elements is dot products between gradients. So in particular, what we're going to need is we'll write a function f and another function g in the hat basis, and we need to be able to compute the inner product that I've written on this slide here. Now, what does that mean in practice? Well, on a single triangle, that means that I need to be able to take the inner product of a hat function and itself at that vertex, and as well as a hat function at one vertex, inner producted with the gradient of the hat function at another vertex. So let's actually work those things out. So let's give ourselves some space here. So again, I'm going to draw us a triangle, nice and big, so that we've got space to work with. So here's V1, V2, V3. And so far, what do we know? We know that the gradient of f is equal to the edge 2, 3 perp divided by 2 times the area of our triangle. And now we have to do two cases, right? Because we're going to integrate these gradients dot producted against each other. Essentially, there's two different things that could happen. It could be that both of the gradients are taken at the same vertex, or another one could be like the gradient of the hat function at this vertex against the gradient of the hat function at some other vertex. So we need to do two different cases. So let's do the first one, which is the same vertex twice. So in other words, remember we have exactly the same scenario. So we have a function which is 1 at vertex 1 maybe, and 0 at vertex 2 and vertex 3. And we want the following, right, which is the integral over our triangle of the dot product between the gradient of our linear function just with itself. That's going to be one piece that we need. Okay, well, remember that this gradient is constant over the whole triangle. So this is really equal to the area of the triangle times the norm of the gradient of f squared. But we just proved that the norm of the gradient of f is 1 over its height, right? So in particular, what that means is that really we have area over h squared, like that. But okay, so what is area? It's 1/2 base times height. So we can write this as base divided by 2 height, like that. And if you go back to our lecture on computing curvature, we'll see that we actually showed a formula for precisely this. In particular, if I label these two angles as alpha and beta, well, then what we showed back in our lecture on curvature is that the ratio of the base of a triangle to its height is equal to 1/2 cotangent of alpha plus cotangent of beta, this pesky cotangent function showing up again. So again, essentially, what have we done? Well, we've gone over the case where I want to know the norm of, or rather just a hat function dot producted with itself integrated over a triangle. Okay, so let's clear out some space. Okay, so let's do that second case. Oops, I erased our triangle. All right, that's okay. So let's put our triangle back here. So here's our 3 vertices again, just like before. And remember we have angle alpha and angle beta, like that, right? So the second case is going to be taking the inner product of 2 different half functions. So for example, the gradients of 2 different half functions, like maybe the gradient of the half function that starts at alpha and goes toward the edge on the right, and the other function that starts at beta and goes to the left, right? So we have 2 different hats. Okay, so now we need a slightly different line of reasoning, but only slightly. For some reason I keep getting it wrong, but in any event, what do we have? Well, now we have the integral over our triangle of the dot product between the gradient of the hat function that's 1 at the angle with alpha and the gradient of the hat function that's 1 at the corner with beta, d area. But once again, these are just 2 different constant vectors for our whole triangle, right? So I can really think of this as A times the dot product between these things, like that. Okay, so now let's label a few more things just for convenience. In particular, we'll say that this edge has length L1, this edge on the left has length L2, like that. We'll label the corner here theta. Okay, so first of all, what are the gradients here? So the gradient F alpha is going to look like this, right? So this is the gradient F alpha, right? Because it's perpendicular to the opposite edge. That's what we showed before. And similarly here, we're going to have that this is the gradient of F beta, like that. Okay, so in particular, let's take edges that are coming out of our upper vertex. So we'll call this edge E2 and this edge E1. And these are just vectors that point out like that. Okay, then what is our gradient vector? Well, remember that it's the edge rotated 90 degrees counterclockwise divided by 2 times the area, right? So we have the area of the triangle like that. And we have to be a little bit careful with the sign here because we want them to point inside and we have a counterclockwise rotation. Okay, so the gradient F alpha, if I rotate E1 counterclockwise, it's going to point out of the triangle. So we actually have minus E1 perp divided by 2 times the area. And now here, if we rotate counterclockwise, we get it in the right direction. So this is E2 perp divided by 2 times the area, like that. Okay, so in other words, what we're going to get is, well, we have a 1 over 4 area squared and an area here. So we get 1 over 4 area. There's a minus 1. The inner product between E1 perp and E2 perp, like that. But they're both essentially E1 and E2 with the same matrix rotation applied to both of them. So this is the same as the inner product between E1 and E2, like that. And what is the inner product between E1 and E2? Well, okay, so it's a dot product. So it's the length L1 times the length L2 times cosine of theta, right? So this is equal to minus 1 over 4 times the area times L1, L2 cosine theta. Now, we've got a lot going on here. We need to simplify this. So we've got 1 over area, we've got L1 times L2, we've got a cosine. Let's see if we can clean things up a little bit. So in order to do that, I'm going to draw one more thing, which is going to make our diagram a little ugly, which is the height of our triangle. Call that H, okay? So why am I going to do that? Well, remember that area is equal to 1/2 base times height, right? So particular area is equal to 1/2 times L2H, like that. Let's plug that formula in. So we're going to put 1/2 L2H here. And what do we get? We get a minus 1 over, so we got 4 times 1/2 gives us a 2. The L2's cancel, but we still have the H. Now we have L1 like that, cosine of theta. So now we're getting a little bit closer. All right, so we have L1. I'm checking my formula really quick to make sure we're in good shape. Yeah. All right, so now let's take a look at the ratio L1 divided by H. What is that? Well, we've got a right triangle. We've got L1 and H and a right angle. Take a look at sine of theta. Sine of theta is opposite over hypotenuse. So sine of theta is H over L1. I'm betting there's a simpler way to derive this formula, by the way, but this is the one that I worked out, so now you're all stuck with it. We have an L1 over H, so really this is equal to minus 1/2 times cosine theta over sine theta, which is the same as minus 1/2 cotangent of theta. Okay, so what did we just show here? We showed that if we have two different hat functions on a single triangle, meaning just two functions, one of which is 1, 0, 0, and the other is 1, 0, 0, and linearly interpolated in between, I can take the inner product of their gradients by just integrating that dot product along the triangle. And after basically just a trigonometry argument, what we end up with is this kind of nice formula that really the inner product of two hat functions is just equal to minus 1/2 times cotangent of the angle that isn't at either one of the two hats. So it looks a little complicated, but it's really not so bad. Okay, so let's clean up this board a little bit, and then we'll show it to you on the slide too. Okay, so let's take a look at some slides that are going to summarize the calculation we just did. Essentially, again, what we're after is this integral on the top, specifically when f and g are written in hat basis. But here we're just working on one triangle. So a hat basis is just basically a linear or an affine function that's 1 at one vertex and 0 at the other two vertices. And so we showed essentially two different formulas. One is the norm squared of the gradient of the hat function integrated over the triangle, which gave us 1/2 times the sum of cotangents. And the second thing we did was show we have two different hat functions at two different vertices. Take their gradients, inner product, and integrate over the triangle. We get yet another cotangent formula. This thing is essentially appearing everywhere. Okay, so that does it. We've now done all the calculations we could do on a single triangle, but at the end of the day, we want to work on a triangle mesh, like a surface. So what do we need to do? Well, again, a hat basis is essentially that linearly interpolated function when you restrict it to any one triangle, but it's also, you know, the same interpolant on every single triangle. So what does that mean? That means if I have a vertex P on my mesh, well, then if I take the gradient of the hat function, I'm going to get one vector in every triangle in its one ring. Notice that the gradient is 0 in the farther rings out because the function is just constantly 0 out of there. So what do I get? Well, I just end up with a bunch of sums of cotangents, which makes sense. All I did was take our formula we just derived and sum it over the one ring of triangles. And similarly, okay, well, if I want to take the hat function at a vertex P and the hat function at a vertex Q, for one thing, if P and Q are not adjacent, the inner product is 0. That's easy to see. And when they are adjacent, essentially we get two terms, right? One from the triangle on the left and one from the triangle on the right. And in both cases, we get this same cotangent formula that we derived in case number 2. And once again, let me remind you that this is pretty much very similar to the operator that we got when we took the gradient of surface area. It's almost identical to our calculation there. In fact, my suspicion is we could almost just reuse that proof line for line with almost no change. Okay, so what does that lead us to? Well, we end up with a matrix, which is extremely famous in the world of geometry processing, known as the cotangent Laplacian. And here you are looking at it in its full glory. So again, how did we define the cotangent Laplacian, Lij? Essentially, Lij is the inner product of the hat function at vertex I with the hat function at vertex j. So when I or j are equal to each other, you get the sum over the one ring of our vertex of these cotangent values. And when I and j are adjacent, we get, you know, the second formula, like what I'm illustrating for you on the bottom here. And when I and j are not adjacent or the same, you just get 0. And these are all the possible ways that you can inner product different hat functions at different vertices on our mesh. So now we've done the heavy lifting. Now we basically have all the objects we need to solve a Poisson equation on a triangulated domain. So here, let's say I want to solve Laplacian f equals g, and moreover, I've written g, and I'm willing to write f as combinations of hat functions on some triangulated domain. So what we're essentially after are weak solutions to our PDE, meaning that rather than asking Laplace f equals g, we're asking, you know, the integral of Laplace f against the test function phi is equal to the integral of g against the test function phi. But specifically for f, g, and our test functions, we plug in this hat basis, h. Okay, so when we do that, I'm essentially just reviewing the calculation we did at the beginning of lecture, so I'm kind of zooming through these slides. Well, what do we get? Well, when we plug in our form for f, right? F is the sum of vk times hk here. If you go all the way to the bottom, essentially what we've shown is that integrating the Laplacian of f against a hat function hl is just this matrix L that we just derived multiplied by the vector v of coefficients that are giving us our input function f. In fact, if we stack them all together, then we can get the function f integrated against all the hat functions in one shot, and that's just L times v. Okay, so far we've only taken care of half our Poisson equation, right? We wanted to solve Laplace f equals g. I've integrated the left-hand side against the test function. I also have to integrate the right-hand side against the test function, and I didn't tell you how to do that. And in fact, mathematically, that's a bit of a headache. And the reason is that we have two different hat functions, like what I'm showing you on the left. If we multiply hat functions together without taking their gradients anymore, right, that's the right-hand side of our expression here, what we get is not a constant, we get something quadratic, and that's actually kind of annoying to integrate. Now, there are two different ways out. One is just to integrate this quadratic thing along a triangle. This is called consistent FEM. A second way out is to do a bit more approximation, and we'll cover both very briefly. So if we want to compute the actual integral of these hat functions against each other without their gradient, what we get is something called the mass matrix. And the mass matrix is defined as this thing that I've shown you on the slide here. So the element ij here is just the inner product of hat function hi with hat function hj. So the diagonal elements are like the squared norm of hi. The off-diagonal ones are the overlaps, just like we had before. We could go through a very similar proof to what we just did, but I think you guys get the idea of these kinds of proofs. It's just lots of trigonometry and knowing integrals and so on. What you end up getting is, oops, that should be mij instead of aij. And we'll pause for a second. Fixed through the magic of video editing here. Essentially, after we crank through that calculation, you actually get a pretty simple formula at the end, which is that the diagonal elements are equal to the area of the triangle divided by 6. The sort of integral of two hat functions that share an edge against each other is the area of the triangle divided by 12. So if we again sum over the one ring of each vertex, we get a formula like what's on the slide for our mass matrix. So this gives us what you might call a non-diagonal mass matrix or a consistent mass matrix. It has a lot of nice properties. In fact, one of my own research papers proves some nice things about this matrix. So for example, some of the simpler properties of this matrix are that the rows sum to the area of your one ring of a vertex divided by 3, which kind of makes sense, right? Because it's like taking the area of every triangle and distributing it among the 3 neighboring vertices. It only involves a vertex and its neighbor, and it kind of partitions up the surface area. Like if you sum up all the elements of this entire matrix, what you'll get is the surface area. I'll let you convince yourself of that at home. Now, from a linear algebra perspective, one kind of headache here is that this is not a diagonal matrix. It's like yet another big sparse matrix that I have to work with. And in fact, when you apply M to a vector, in some sense, it's like sharing information among adjacent vertices, which can kind of blur out a signal, which sometimes is undesirable. So it turns out that a very common thing is to actually use an approximation of the mass matrix, which is diagonal. And you can motivate that by the following little formula. So let's say that I want to integrate a function on a surface, and I write that function in a hat basis, right? That's our first line here. Well, okay, so the integral of f is just the integral of this linear combination of hat functions hk. We can think of that as being multiplied by the number 1. A very complicated way to write down the number 1, which is our second equality here, is that it's the sum of all the hat functions. And that's just kind of by definition. And now if you push the integral to the inside, what you get is m times v. So at the end of the day, if I want to integrate a function written in the hat basis, and these are all equalities, by the way, there's no approximation, I get this expression at the bottom of the slide, which kind of motivates that really kind of what's going on here is that the mass matrix just has to do with integrating functions. So one common approximation is something called the lumped mass matrix, where instead of using that off-diagonal formula I showed you before, we use a matrix whose diagonal elements are kind of like the areas of little cells that we've used to partition up the surface, where each cell is associated to one vertex of the mesh. This is the dual mesh, and it's something that'll come up again and again in our discussion here. it turns out this doesn't make a very big difference for smooth functions, the action of this matrix and the consistent mass matrix, but it's easier to work with. And there's a little bit of mythology out there that somehow working with this matrix gives you a sharper solution to Poisson equation. It's not 100% clear to me what that means, but it is something you hear a lot in practice. Though there are many choices for how to come up with the area of these dual cells. One very simple one is to just take the area of every triangle divided by 3 and assign it to each of the vertices, and just sum those up down and put them on the diagonal of your matrix. Geometrically, that's kind of like finding the barycenter of your triangle, making this little subdivision here, and constructing your dual cell that way. There are fancier dual cells that come with Voronoi diagrams, or even an entire theory of orthogonal duals developed by Fernando de Gois in his PhD thesis, which is really interesting, associated with optimal transport theory and a lot of other kind of fun areas of research. In any event, if we step back 10 feet, at the end of the day, what we need to solve the Poisson equation is a Cotan Laplacian and a mass matrix of some sort. And then what we've essentially showed in today's lecture is that solving this smooth system of equations ends up being just a matrix solve, like what's on the right-hand side. Of course, one detail here is for the Poisson equation specifically, you need the right-hand side to integrate to 0, or else you're not going to have a solution. But that's just a detail of this particular PDE, and less important for finite element method more broadly. Now, an important detail that we've omitted, of course, is boundary conditions. My postdoc, Oded Stein, is an expert in PDE boundary conditions, and maybe we can invite him to give a guest talk in this class. Essentially, nothing too miraculous or special happens in the boundary condition case. We just have to be careful that when we compute our integrals against test functions, we incorporate whatever boundary conditions we need. That's basically the only difference. And so that's something to do with the transition from our strong form PDE to the weak form PDE, which is the one that FEM is working with. Now, if we want to compute eigenvalues, I think I'll let you guys work out how to do this in finite element method from home. Essentially, what you're going to end up getting is that eigenvectors look like Lx equals lambda mx. So I'll let you guys figure out how you can compute eigenfunctions of Laplacian using first order Galerkin FEM. Incidentally, notice that I've left out the smallest eigenvalue here because it's 0 for the constant function, which isn't too exciting. But this is machinery that's going to allow us to compute eigenhomers, like the vibration basis for different surfaces. Now, one thing you might notice is that we used a really boring basis for functions on our surface. The half functions are just linear. There's a really fun website that I encourage you guys to poke around in. It's actually, they also send out a poster. It's on my graduate student's wall. It's the periodic table of finite elements. And basically, there are all kinds of different finite element bases out there. Daniele Pinotto and other colleagues in geometry processing are showing that there's often a lot of value in not just using this piecewise linear hat functions that we know and love, but actually using, for example, higher order polynomials to get more accurate solution to PDE on surfaces. Now, we spent the entire lecture today deriving Laplacian for functions on triangulated surfaces. The story that we've cooked up really carries over, for example, to tetrahedral meshes without any change. You just need to work through to come up with an analogy of that cotangent formula. In an extra lecture segment, we're going to talk about a popular formula for Laplacians on point clouds that gets applied a lot in the machine learning world. But since we're a little low on time, we'll defer that to the extra lecture segment for you to watch at home. I guess you're watching them all at home, but you can watch this one separately or optionally. And essentially, point cloud Laplacians are tricky because now you don't have topology. There's nothing you can integrate over. So you need some other strategy for developing a matrix that kind of acts like a Laplacian might. Incidentally, for point clouds specifically in 3D, just this year there was an interesting research paper that proposed another alternative. I'll send you there if you want to give it a read. Okay. So with that, we'll conclude our discussion. I think the high-level point here is that Laplacians are not just interesting theoretical objects. We can actually approximate them in practice. So today we worked through the details of how to develop a Laplacian operator that makes sense on a triangulated mesh, or just on a mesh more generally. Really, this FEM strategy is quite broad and just requires cooking up a set of basis functions and then integrating them against each other, and I guess integrating their gradients against each other. So in our next lecture, now that we have a discrete Laplacian operator, we'll go through all kinds of applications where such a thing will be valuable. And hopefully I've convinced you that it's possible and indeed pretty easy to approximate the Laplacian just using sparse matrices. We'll see that a very similar thing is true for point clouds in our supplemental lecture. So with that, I'll see you next time.